started. All right, so it's 2012 0423. Okay, I'm just going to write, a part of a program. So your thread program is going to look, something like this. Thread function, and it takes void pointer as its parameter. I'm going to skip a lot of the code here. So depending on how you want to do things, some people can decide to do something like this. Okay, do and then have a while condition here, and then we'll keep in this loop as long as the counter is less than a certain value. So I'm not even going to fix it to 20 or 19 or whatever. I'll just fix it to k here. So we have a lock here, and then we have print, increment, and unlock the other thing here. So that's kind of typical of what a program may look like for this homework assignment. The problem is let's just say that. Okay, let me use the line numbers here. Okay, so what happens when line 7 increments the counter to k minus 1? That's the question. Now, it doesn't seem to be that big of a deal, right? I mean, if line 7, which is the increment statement, if that increments counter to k minus 1, that means it can go one more iteration. But that's not true, because here is what can happen. Okay, two things can happen. Okay, so let's take a look at what two things can happen. One, okay, the other thread does not get control until this thread gets past line 10 and back to line 5. Okay, is that okay? Does everybody understand this statement? Because after we evaluate, after we do the increment, so that the counter becomes k minus 1, it is possible, entirely up to the kernel to decide. It is entirely possible that we can do the unlock the other thread, but the kernel can decide not to let the other thread execute, and then let this thread to continue to execute past line 10, and then because counter at that time is k minus 1, counter is less than k, and therefore it will go back to line 5, and then only at that point this particular thread will lock. That's the first thing that can happen. But you can also have a second condition happening. The other thread gets control as soon as line 8 finishes. Okay. Now, how would that impact the behavior of this particular program? In the first case, you will basically print one more value, regardless, because by the time you lock, it's already on line 4. And when you're on line 4, it's going to unconditionally print, increment, and then do the whole thing one last iteration. In the second condition, if the other thread gets control as soon as line 8 finishes, because you do have to unlock the lock for the other thread first, that means the other thread is going to go through its iteration, increment, so that by the time you get to line 10, guess what? Counter already is not less than k anymore, and then you will perform one fewer iteration. So let me just explain that part here. Then from this thread's perspective, when it gets to line 10, counter is no longer less than k, and the loop exits. Is that okay? I mean, does that adequately describe the two scenarios that can happen? We don't know which one's going to happen, because it all depends on the scheduling mechanism of the kernel. The kernel can decide, hey, as soon as you unlock another thread, we'll let it run, or the kernel can decide, well, the time slice has not expired yet. I will let this particular thread continue until its time expires or until it gets all the way back to line 5 where it locks itself. So that means the behavior of this program can go either way, but depending on which way it goes, it can count one more, it can print one more line or one fewer line. Okay, now in this program, obviously nothing is going to explode or break or cause people to die in the process. But you can imagine if you have something like this controlling heavy equipment or anything that is critical, bad things can happen. Going through one more iteration can be an issue. So how are we going to fix this problem? Yep.
So would it work if you if you had an initial lock before your do while loop, and then put one right after the unlock? Would that fix this problem?
You mean have a lock between which two lines?
Between 2 and 3.
Between line 2 and line 3. Do a lock here.
Right, and then do a lock between 9 and 10.
Line 10 and 11?
9 and 10.
9 and 10. Okay, so we want to do a lock here?
Yeah. And take out line 6. And then take out line 6.
And take out line 6. That is not going to work because you still have a narrow window where the other thread can come in.
Even between lines 9 and 10, you have that window that's going to mess you up?
That's still a window.
Okay.
Because, okay, the proposed solution is to put the lock here, so initially lock it, not do it in the loop, but you still have to unlock it, over here. So that's not going to, solve the problem.
Why
okay.
not?
Okay, let's see. Let's take a look here. Let me save this first, and then we'll copy this. Okay, so this is a potential solution. So one potential solution is to put a lock here, remove this one, and then put one here. Is that what you're saying?
Yeah.
So that means, when you check this condition, it is still unlocked from the other side.
Seems like the other thread would have gotten to a lock.
I think that would work.
That would work because by the time you get to this lock here, the other thread would have locked itself immediately, and there's no increment that is possible. So yes, this approach would work, but it doesn't really address the issue. It works in this case because of the way these two particular threads interlock with each other.
Right.
But it doesn't really address the issue of counter can be updated, quote unquote, in the background by somebody else.
Right.
So yep, go ahead.
Could you have a temporary value of your counter so that right after you increment it, you save a temporary value that you then use to check?
Yes, but that still does not address the issue because what you want to check with this counter value is the value that is updated after it is updated by the other thread. Because the other thread is going to update the value of the counter. Now there's another way to fix this problem. The other way to fix the problem is to understand who you are. Because we have two threads. One thread is only supposed to see even numbers, and the other one is only supposed to see odd numbers. Is that right? So that means the one that is supposed to see even numbers should not compare to an odd number. It doesn't make sense. So if you force a thread to always compare to either odd numbers or even numbers in this particular case, then you can also fix that problem this way because you know that what is the last number that you are supposed to see. If you have seen the last number that you are supposed to see, then you should quit. So for this particular program, that would be a good solution to fix that problem. But it still doesn't it still does not address the overall issue that counter is a global variable and somebody can change it in the background. So what you suggested, putting a lock first, copy the value of counter to a temporary variable, unlock, and then return the temporary value would be the appropriate solution. Okay, let me describe that solution here first. So what you do is you say, this is int, and then we say, counter get counter value. So what you do is you put, a new mutex here, and lock counter mutex, which has nothing to do with the thread mutexes. So this would be a new mutex for the entire program. And then you have your own local int copy of counter, but don't do anything until you have locked it here. Then you can say copy of counter equals counter, unlock counter mutex, and then return copy of counter. So what this does is to make sure that when we are making a copy of counter, nobody else can be changing in the background. But that also means when you increment it from the other one, you also need something similar. In other words, you need another subroutine to do the increment counter value, and it's going to have similar structure in the way that you have to lock counter mutex first, and then you plus counter, and then you unlock counter mutex. So that way, the code that is incrementing and the code that is checking, they cannot interleave each other. Only one can go through. Either you increment or you can check the value, but you cannot check the value halfway, have the other one to increment, and then come back and check the rest of the counter value. This problem does not happen with this particular program for two reasons. One, we have a 32-bit counter, and the increment one by in a 32-bit context is an atomic operation to begin with. It's add $1 to the counter variable in assembly language. It is one single instruction. It is not interruptible, and therefore you don't have to worry about the variable getting half updated, check, and then come back and finish the update. But this would be the proper approach when you have anything that is shared between different threads or interrupt subroutines and signal handlers. But it would not have helped in this case because the issue that we have here has to do with the interlocking of the processes. Any questions?
So your counter mutex is that's a kind of a global?
Yeah. Well, either global or you have to make it a global because it has to be accessible by both subroutines. So it has to be a global one, and you have to initialize it in main before you have anything that can get to either get counter value or increment counter. Is that okay so far? But the other solution, there are many different solutions here. The one more solution is to not use a particular k that is a constant. You can make this limit for this thread. In other words, each thread can have its own limit. If you know that you're dealing with a thread that only deals with even numbers, then you can make this limit particular to that particular thread. We are supposed to count up to 20, but not print the value up to 20, right? So that means for the first thread that is starting with 0, what would be this value? Well, you can make this less than or equal to 18. Yep. So for the first thread, you can make this less than or equal to, okay, limit is 18 for the first thread. And 19 for the second one. Does that make any sense? So that will also, address this issue, because even if something is updating in the background, it's okay because I only have to check against, where I am supposed to get up to. As long as, I am done with the last value that I have to update, I'm done. I'm just going to exit. Whether someone is updating this in the background or not is not going to be an issue. So there are two ways to fix this problem. Is anyone else experiencing this particular issue? You know, where sometimes, or it will count one more iteration? Yep.
I think I may have run into that. I just didn't understand it, so I just modified the code so I didn't do that anymore. But it was printing like to 21.
Okay.
Would that be that problem?
It's supposed to print up to 19.
Right, right. And then I adjusted
adjusted
my
the
loop
limit?
control by 1, and that brought it down actually 2, so it only printed to 19.
But it is because of this.
Got it.
It is
That's
because
fine.
of this.
I didn't understand why it was doing it now.
Yeah.
That makes sense.
But does everybody understand the original issue? You know, let's go back to the original program and make sure that we all understand what the problem is. Because you know, it's all explained here. Because after you unlock the other thread, it depends on the scheduling mechanism. It is possible that the other thread will kick in right away, do the increment, and then by the time you get to this thread's counter comparison, it is already it has reached the limit already, so it get out. But it is also possible that when you do the unlock the other thread, this particular thread continues to execute. So at that point, counter will still be less than k, go back to the beginning, and then go through one more iteration than it has to, than it should. Yep.
So if my program fulfills the spec right now, is it possible that it can shift back and forth, like kind of be undefined? Or if it's working, then it's okay?
If it is working now, it depends on how you solve the problem. Because if you solve the problem simply by changing this k here,
Yeah.
then it is possible that if the kernel decides to use another scheduling mechanism, then it won't work anymore.
Okay.
So,
Good to know.
yep. Are there any questions about this? I can see some frowns.
I'm just adjusting it because mine just worked fine with that, and I never thought about it.
It is possible that you're not using this particular logic. Remember, it is specific to the logic as well. When you
No,
look at,
I am using that logic.
because if you look at thread 1, this one will not have that problem to begin with because the locking is happening here and then the unlock is here. By repositioning the unlock and the lock so that they are sequential like this, instead of spread over the condition evaluation, you could fix that problem too.
No, I have it the other way.
You have it the other way?
And it worked fine, but maybe it's just the timing.
It's the
Just not
timing.
lucky.
Yep, it is the timing.
Would you explain again to me why this works? 'Cause I'm starting to understand the problem that you're talking about, but I still don't understand why Kathy's solution actually works. Because why is putting the unlock and lock sequential? Why does that
Okay,
protect us?
it has to do with, okay, let's do this
This is
side by side.
unlocking the other thread and then locking this thread, right?
Right, okay, let's do a side-by-side comparison. So we'll do a thread.c and thread1.c. I think it's a -O to open both at the same time. I want to do it side-by-side. Is it uppercase O's or side-by-side? Vertical split, there we go. And then we'll go ahead and do it like this so we can. Okay, this is a good side-by-side comparison. The first one has the lock here and the unlock here. The problem is, right after the unlock is the comparison to determine whether to go for another iteration or not, and then the lock is all the way up here. The second approach has the unlock here, and then immediately do the lock before the comparison happens. Now that is significant because this lock is guaranteed to stop this particular thread. In other words, this particular thread will not evaluate the value of counter until the other thread executes.
Right.
And I'm still thinking whether this can lead to that problem or not, because if you unlock the other thread, then there's still an uncertainty because the other thread can either go through the condition right away.
But the increment's already happened.
The increment has already happened. That's right. Yep.
Couldn't you just use a sleep after lock? Wouldn't that, allow you to be able to do it right?
So you're basically using a delay to make sure the other one has a chance to do it. It will address the problem, But sleep has, any type of delay like that, you're basically, you're creating a race condition. In other words, you're counting on the fact that within a second, the other thread will be able to finish its own operation, which may or may not be true. Now, I know 1 second is a long time, but in a real world program, you cannot afford to have a wait for a second. So in that case, how much time do you want to allow? But that's a race condition. It depends on system load, what other things the system is doing. So you're basically creating a race condition where in most cases it will solve the problem, but in very rare occasions, for some reason the system load is really heavy, or if you write a Java program, garbage collection happens and everything locks up, so the delay that you specify may not be sufficient anymore. So that problem will still happen. It's just that it is unpredictable when it's going to happen. Also, getting back to this one,
Well,
yeah.
Because this is going to happen the first time, right? But the other one's going to start out locked, and so this one's going to lock, and then it's going to come down. It's going to unlock the other one, then it's going to lock, right?
Yeah, it will unlock the other one. What I'm thinking is, whether it will still change the order of things,
Yeah,
whether it can still do the wrong thing here.
So the
and
other
the answer is no, because if you unlock here, with the other one, it doesn't matter whether the kernel, gives the other thread, execution right immediately or not, because you will still have to eventually get to this lock here and wait for the other thread to unlock you. So by the time you are unlocked, the counter would have been updated by the other thread already. So that's why this approach always works.
Well, let me just run this through, because if you go through the first time, you're going to come in and you're going to unlock the other one, then you're going to lock and stop. So the other one is locked.
Right.
So it's going to come through, or it's going to start. It's going to unlock from the block that's outside the loop.
Right.
And then it's going to come in.
No, but this only happens once.
Yeah, so the other one had just started there, because this is the first time we run through, so.
Thread B should start there, right?
So thread B starts there, and then it comes through, and it does the increment. The other one's stopped.
The other one has stopped already.
Yep, because on its first
Well,
time
the other one may not have stopped because between the unlock of the other thread and this lock here, anything can happen.
Yeah, but it's going to stop. It's going to work.
But there's no evaluation of this condition in
so it's
between,
okay.
and that is the key.
Yeah.
Okay.
So the other one, thread B is going to come in and it's going to do the increment, and then it's going to unlock thread A, and then it's going to do a lock, but it's not going to stop there. It's going to go through and do the equal, or it's going to go through and do the check. And so when thread B or thread A have maybe had a chance to go through an increment already before it gone through and done the check.
It's not possible because the increment has to happen before the unlock. And then the process, and then that particular thread has to lock itself. So that means there's no chance of, there's no alternative whether this can happen before or after the counter gets incremented. That's the problem. With this code, there's a probability we can go either way. With this code here, it depends on what this is going to do. It is possible that right between the increment and this part here, there's another increment happening because the other thread executes. Or it is possible that the other thread doesn't have a chance to increment, so you're looking at your own counter value. But the other one doesn't have that chance because by the time between this one, the increment, and also the checking of the limit, there's no way, you're always guaranteed that the other thread has a chance to update the counter.
But I kind of have the same question I think that he brought up. It's like, if thread B is unlocked, then once it hits the lock in the loop, it can still go through there because it's just locking up after itself. And then it's going to check, it's going to evaluate, drop through the loop again, and when it hits the locked lock, then it blocks. Is there an error in what I'm saying?
Okay, we know that the two threads there's only a very short amount of time where they can both run. Okay. And that is basically between the time that you unlock the other thread and the time that you lock this particular thread. That's the only window where both threads can execute in parallel. Is that okay? Right?
Yeah.
Okay, so in this particular case, it really doesn't matter because if you unlock the other thread doesn't run automatically and you stop here, right?
But will you always stop there? What if you're unlocked?
What if you are unlocked?
Yeah, then
But you're
gonna-
always locked. This should always block the thread that is running it.
Well, doesn't.
Because
but what
otherwise
we're
the
saying
interleaving
is-
doesn't work.
But
That's
doesn't
true.
thread B, when it first starts out, it's locked, so when it comes down, it hits the lock and it stops.
Right.
And then thread A is going to unlock it.
Yeah.
Right?
And it's gonna come down, and it's gonna increment, then it's gonna hit the lock, and it's not gonna stop on that lock, because it hasn't hit the lock the second time yet.
Yeah, I'm with him right now as far as
So
I
it's gonna
know.
come back up, and then it's gonna increment
No,
again
no,
before
no,
it
no,
locks.
okay, okay,
before it
okay,
stops.
let's say this is thread B, okay, the second
Yeah, yeah.
thread. Thread B is gonna block here initially, because that's how we set it up. We
Uh-huh.
lock that mutex
okay.
before we
That's right.
start the thread.
That's right.
Okay, so
Got it.
when thread A unlocks thread B, it will be able to get past this lock here. Then it's gonna do the print, it's gonna do the increment, and then it will unlock thread A again.
And its mutex is already locked. That's
And then
fine.
when it gets to here, it has to stop because at this point
It locked outside the loop. That answers my question. It can't drop through there because it's blocking at lock, but as soon as it's unblocked, what does it do? It locks itself. So it drops through that lock, but not the lock within the loop. I think I had the same question as you. Because it's blocking at lock. So the first thing it does when it's unlocked, it locks.
Okay, so it locks after it's unlocked.
Exactly.
because each one can
First
only
thing
be
it does.
unlocked by the other side.
Okay, yeah, that makes sense. It's just getting the order of the
Okay.
locking.
Yeah, but this is one way to look at it. You can use my favorite tool for this is just a spreadsheet.
Yeah, I should
Okay.
get confused again when it actually executes the lock command, and
Okay, so here's the
when it blocks and when it executes the lock command.
okay, what is this? Oh, this is assembly language programming. Some of you may still remember this stuff. All right, so we'll go ahead and create the two scenarios, okay? Because this is really a good way to visualize how things can happen. Okay, so this is thread A, and here's thread B. Thread A is the one that counts even numbers, and thread B is the one that counts odd numbers. And I should change the sheet here and change the name to this is this reflects thread.c. Okay. All right. So thread A is pretty easy. Thread A goes through the lock. When it goes through lock the first time, it's not going to block itself because the mutex is unlocked to begin with. So it's okay for thread A to go through lock. Then it's going to print, it's going to increment, and it's going to unlock the other thread. This is where problems can happen because when it unlocks the other thread, two things can happen now. So I will describe this one. Okay, let's change this name to thread.c scenario A. In scenario A, we'll say that thread B is now officially unlocked. However, the kernel decides not to give thread B a chance to execute and decides that, oh, well, thread A can continue. Now, if thread A continues, then it will compare counter to K, and then it will go back to lock itself. And only at this time, the kernel says, okay, since thread A really has nothing to do at this point, nothing that it can do at this point, we'll go to thread B.
It's gonna block, right?
Right, it is blocking. So then thread
And
B
then-
will get to execute. So thread B will be able to get past its lock call, which it was blocking to begin with, but now it is unlocked by thread A. It goes through its print, go through its own increment, and it will go through the unlock other thread, and then it goes to its own counter is less than K, and then it goes back to the beginning of the loop and then lock again. So this is one scenario. I'm going to use sheet 2 to describe the second scenario.
So if it's run the lock command and then it gets back, or the lock function, when it gets back to the lock function, it blocks before it calls lock again, right? Or before it actually
The
performs
key is
lock.
right after you unlock the other thread, what's
Uh-huh.
going to happen? That basically is the big question. Now let's go to thread B, and we are going to take a look at thread B. I mean situation B. Situation B. Now in situation B, it is possible that we don't get to these two until later. So that means thread B gets to go through at least this much. And then thread A comes back and finish the rest of the operation. Now that is a significant change because in scenario A, the counter value that you're comparing is your own counter value. This is the same value after you increment, and you're using the same value for the comparison. In situation B, this is the value that you last saw in counter. But by the time you get back to compare to K, it is already incremented again by the other thread. So the interleaving makes it possible that sometimes the counter value will be one more than what you think it should be. And therefore the boundary, when you set the boundary, when you set the limit, you cannot set a constant limit anymore that will work in both cases. Unless you have one boundary or one limit per thread, then it's okay because each thread says okay, I know that this is my last number. If I have not seen my last number, I'm going to go through another iteration because I know that I'm supposed to only see even numbers, and then the other one would say I'm only supposed to see odd numbers. So you can customize the limit per thread to solve that problem. Now let's take a look at Kathy's solution. Now Kathy's solution is going to solve the problem because the increment cannot happen between the unlock and the checking of the condition. That's the solution. So let's go ahead and run through that scenario.
Except that I just ran the code and it introduces a new problem. I just ran the code and it introduces a new problem, but we'll get to that after you go through this.
Okay. So thread A is going thread 1C, which matches the name of the source code that we went through today, is going to once again, we have thread A, which is even for the even numbers, and then thread B, which is for odd numbers. So thread A is the one that will first unlock because it's the even number thread. It will do the print. It's going to do the increment, and then at this point, it's going to unlock the other thread. Now, when you unlock the other thread, you have two ways to go: whether the other thread gets to execute right now, or whether it gets to execute later. So now we're going to create the two scenarios: thread 1.c, scenario B. Now the scenario A and the scenario B are just what we can think of at this point, because the interleaving obviously can happen in more flexibility than we have just talked about, because it can happen basically anytime. Okay, in scenario A, after you unlock the other thread, nothing happens. Okay, this thread continues to get to the lock operation here, and then at that point, thread B will get its own chance to execute. So thread B will go through lock, print, increment, unlock the other thread, and then it will lock itself. By the time it locks itself again, it's this. You have no choice but to come back here. But to come back here to do the counter comparison. Right? So that means between the time you do your own increment from thread A's perspective to the time you check the counter value, the other thread is guaranteed to have incremented it at least once. Exactly once, I should say. Let's look at scenario B, where as soon as you unlock the other thread, it gets control. So when it gets control, it will finish the lock call, it prints, it increments, it unlocks the other thread, and then it locks again. Right? So now you get back to here to check your counter value to limit. So once again, between the time that you increment and also the time that you check your limit, thread B is guaranteed to have incremented the value once. So you don't have the possibility between these two scenarios where the checking of the counter value can happen before the increment of the other one, or it can happen it can happen. There's no additional incrementing in this case, and in this case there's one more increment before you check the counter value. But with the other program, there's no chance that they can interleave in a way that is not predictable.
Okay, so the problem I had when I ran the code is it got to 19 gorgeously, and then it just stopped execution. And I'm thinking that it's possible that there's nothing to unlock that last
Exactly.
thread.
Yep. Because you have one last lock that is not unlocked. Because the last action is to lock it yourself.
Right.
So whatever thread is the last to get out, no one is going to unlock it.
Right.
So you have to do another unlock after your loop.
That's what I did. Is I unlocked the other thread's mutex just to make sure it had a chance to check the counter.
But that would be kind of because you're doing one additional unlock at the very end after the loop,
Right.
just to make sure that the other thread has a chance to finish up.
Right.
So that would still be, if you count the number of locks and unlocks, it would be correct. And that's because you have one extra lock on the outside.
Okay.
But you can see, but now I think you guys can start to see, all the potential problems, that can be associated with, multi-threading, because it all depends on the scheduling. So are there any questions regarding, this particular issue? And this is only the tip of the iceberg when it comes to multi-threading programming. Yep.
So I just wanted to clarify in my mind, when you come to the lock call,
Mm-hmm.
if the mutex is already locked, if the mutex you're gonna pass to that call is already locked, when it gets to that call, it goes inside, but before it blocks, before it'll actually relock it, right? So something unlocks it, and then it starts executing again. It's going to lock again, or it's going to do a lock. So the next time it comes back to that, it's called again, then it blocks. So it's then it will relock. Start it.
Are you referring to thread 1 or thread?
Just in general,
In general?
for the lock call.
The lock call is our mutex lock.
Yep. So it's gonna if the mutex has been blocked and it runs into the lock call, it's gonna block.
Right.
And then when that mutex has been unlocked, it'll lock it again, and then it'll continue execution.
Right. It stays locked basically.
Basically
in
stays
our program, both locks, quote unquote, stays unlocked, all the time, so that when a thread gets back to its own mutex lock, it always blocks. It's only waiting for the other thread to unlock it. Okay. Are we kind of doing okay with this one? I think the best solution is really change the counter limit, so that each thread gets its own limit. That's one way. Let me think about it. Yep, that will solve the problem, because whether you have one additional count increment or not, after the unlock, really does not matter anymore, because you're only comparing to your own last value, which is okay, because whether the other one has one additional increment, you're still going to exit the loop properly. Okay. Any questions about this stuff?
So they still share the same counter, they just have different limits on the loop?
Correct.
Okay.
So you basically make this K specific to the thread itself. It becomes a part of the data structure that you pass into the thread.
Okay.
That's one possible solution.
Okay.
Yeah. The other solution is to use this method here, but then you need one extra unlock at the end because one of the threads require one last unlock so that it frees the other thread to exit to.
So you.
But the other thread will just be executing an extra unlock operation for no reason because the other thread, the first one is already gone by the time the second one goes through the extra unlock outside of the loop.
That's what my program does.
Yeah.
But you would make it a variable within the structure representing each thread, or that gets passed to each thread. You'd make the counter limit a
Right.
variable inside the structure.
Yes, because it is thread specific. It depends on which thread we are dealing
Right.
with. Yep. Okay. Does everybody understand the issues, or at least a kind of a gist of what we are talking about? It has to do with the interlocking of the threads, which actually brings up a very good. It's a good lead in to what I'm going to talk about next. So what I'll talk about next is going back to my website. I told the people who went to the lab already that today I'm going to switch to kind of the implementation and some overall information about real-time kernels and scheduling of threads. Okay, so what we will do is we will start with just an overall discussion of basically what a multi-threading kernel does. In this particular case, it is not Linux. It is just a real-time kernel. Real-time kernel versus a regular kernel, the only difference is a real-time kernel is more time sensitive. In other words, it has mechanisms to handle time in a more reliable way than a non-real-time kernel. You can have a non-real-time kernel basically saying, yeah, we'll get around to it. When we get to it, we'll get to it. Okay, but a real-time kernel has more sense of time than a non-real-time kernel. So here it talks about what a thread is. A process has at least one thread, so we know that already with our own programming. A thread is the context that is necessary to execute code sequentially as specified by a program source code, which really doesn't say much. A process can have multiple threads, but all these threads must share all variables and data structures that are either statically allocated or allocated via dynamic memory allocation. That part we know too, because the heap is shared and the global variables are shared as well between threads of the same process. On the other hand, threads do not share any variables or objects that are stack-based. Is that okay? Does everybody understand what I mean by stack-based? Because I know not everyone in this class has taken cisp453 or the assembly programming class. So is that statement okay, or should I go in and explain some more?
Yeah.
Is okay?
Well,
All
could you
right.
explain a little bit more about the stack? I understand
Sure.
abstractly what it is, but I haven't taken assembly.
Okay. So let's go. Let me just highlight which part I'm trying to explain here. Okay. The stack is it's kind of like a data structure. Every time you create auto local variables and you have parameters, they are all living on the stack. Per invocation of a subroutine, new storage will be allocated for local variables as well as parameters. Okay, and that's what we mean by anything that is stack-based. Now you have to be careful because local variables may not be stack-based. Have you guys talked about this in your C class, in cisp453, that you can have non-auto local local variables.
Static variables?
Static local variables. Has that concept even been covered in cisp453? Let me show you this code. It's better to just illustrate it with a program. Static local .c. Okay, so here we have a subroutine f. Okay. And I have a local variable here, but instead of just saying int something, I say static int I equals, okay, let's say 3. Okay. And for each iteration, every time I call f, I'm going to increment I. main is going to call f several times. Okay, and then return itself. All right. Now, in this particular program, it doesn't print anything. So, in order to see how it works, you have to go into GDB. But if you look at this program, if I did not use the word static all the way up here, this program would just be kind of pointless, because I would be created every single time we get into the subroutine. It will be initialized with a value of 3. We increment it from 3 to 4, and then we immediately return from the subroutine. The local variable ceases to exist. Okay, that's what a auto local variable is. By default, all local variables are auto, which means they only get created when you invoke a subroutine, but they cease to exist as soon as you return from the subroutine. But when you add that magic word, static, it's not the case anymore, because now the local variable I is always there. As soon as you start running the program, the local variable I of f starts to exist with an initial value of 3. So that means the first time we call f, it's going to increment I. It will increment I from 3 to 4, and then the second time from 4 to 5, and then from 5 to 6, 6 to 7, 7 to 8, 8 to 9.
So it just ignores the variable declaration?
It's not ignored, it's just that I is still a local variable from the scope perspective. In other words, you can only get to see or make I visible when you're inside subroutine f. In main, you cannot see it. But it still exists, it's just that you cannot see it. Whereas if you do not use the word static, when you're not in a subroutine, you cannot access it, and it does not exist unless f is called.
Right.
Okay. Now, but this has a huge impact in terms of multi-threading, because if you call any subroutine that uses static local variables inside one of the threads, and the other threads can call the same subroutine, you can have problems. Because it is possible that you're halfway through a subroutine using a static local variable, and the local variable is being used to keep track of something, and then the thread changes. The kernel says, oh, this thread has run out of time, I'm going to start up the other thread. The other thread can call the same subroutine, but because you really only have one I in existence, so the other thread is going to reinitialize I for itself, and then your first thread, or the local variable I for the first thread, is gone. It is destroyed. So that's why there are certain subroutines that are called thread safe, and certain subroutines are called non-safe for multi-threading. It's because mostly because of the use of static local variables. Yep.
Why wouldn't it be initialized 3 every time? What happens?
Well, it's because how should I put it? Because some subroutines try to maintain its internal state, so that because it was never meant to be used in a multi-threading environment, so the first time you call it, depending on your arguments and your parameters, it will set itself up and say, okay, this is the first time I'm running, and this is how I want to initialize everything. The second time and then the third time you call it, due to the changes to the parameters that you use to call the subroutine, it understands, oh, this is not the first time. I'm continuing an operation from the last time. And so it will utilize the static local variable to keep track of its state for subsequent calls to the subroutine. And there are crazy calls like that. I know it sounds really crazy, that the subroutine will use parameters to say, oh, this is the first time and now here's the second time. Go ahead.
I helped someone just over the weekend who was working with the
string
token function.
Yeah, string token.
Exactly that.
strtok string token.
So stupid.
Yet people use it. Yep.
So this a static variable is an example of a stack based.
It is not stack based.
It is not stack.
And that's the problem. It is not stack based. Yep. Because when it's not stack based, it means you're not having one copy of I per invocation. You have one copy of I for all invocations of subroutine F in this case. And recursion is not going to work because recursion relies on one copy per invocation. multi-threading is not going to work either, because you can have f being interrupted in between, and then have another thread to start to call f when f was already in progress by another thread. Yep.
So here you don't change the parameters to the f function call, but f still knows that it's not reinitializing I to 3 every time it's called.
Because when it is static, it is only initialized at the entry point of the entire program.
Okay.
In other words, I gets a value of 3 before main gets called.
Oh, okay.
That's what it has the same meaning as this.
Got it. As if it were global.
It has exactly the same meaning. The only difference between this global I and the local variable I is the scope. The global one is visible throughout the entire program. This one is only visible within the function f.
Okay.
But if you look at the lifetime or the lifespan of the variable, they are exactly the same. Okay. Any questions about this one? No. And that's why global variables are bad. Anything that's statically allocated can have issues. Okay, so that's good. I think, are we doing okay with this one? Variables or objects that are stack-based. In most implementations, every thread has its own stack. Exceptions include, the RTK kernel used by, Zworld, which was my previous employer. I can only say up to 1998 because whatever they do after 1998, I have no idea.
So, okay, so the static variable is a stack-based, or threads do not share variables that are, or objects that are stack-based. Okay.
Static local variables are not stack-based, and
Okay.
therefore, if you want to write anything that is supposed to be used in a multi-threading environment, do not use static.
A stack-based variable would be if
Just
you
auto.
didn't have the static.
Correct.
The static, right.
Or if you want to be redundant, you can always say auto. Auto says the same thing. Auto says, this variable should be created on the stack. The reason why we see auto, or it is even necessary, is because I think in some cases, the default is not specified, or at least at one point in the C specification, it is up to the compiler to decide whether it is auto or static. Because otherwise, it makes no sense that you have to use auto to mean non-static. Because if you do not say static, it should default to auto already, and there's no need to say auto. So I think it's because of the evolution or the changes to the C compiler over time that makes this auto keyword even used to begin with. All right. So are we doing okay so far with this slide? Just general concept of threads, what a thread is. Now, when we come to multi-threading, things can get interesting. Now, this is you don't have to read the entire thing. We can consider a program that runs on the robotic system. Okay, so this is a tiny little robot that has to run around, but you do have a lot of things that are happening at the same time that you have to kind of deal with at the same time. You may have a Bluetooth interface on your robot, so you can open up a dumb terminal on your cell phone to talk to the robot, or at least the robot can report its status on your cell phone. You cannot imagine how useful it is to have a terminal wirelessly attached to a robot when it's running. How many people have the chance of programming a robotic type of toy or whatever? Okay. Would you want to run around with a little tether, with a so that you can just follow the robot and have everything displayed on the laptop computer using the RS-232 cable? Bluetooth, yes. Now, some people would argue and say, but what about an LCD display on the robot itself?
You have to run around and follow the robot reading.
Exactly. That's what happened to some of the micro mice. When I still taught micro mouse, some teams decided we'll make our mouse extra fancy and have an LCD display on it, and then quickly they found out, hey, but when the robot is halfway through the maze, we cannot really read the LCD screen anymore.
I have a solution for that. Mount a projector on it, the ceiling.
Yeah.
So you can just look up at the ceiling and see the whole stats of the robot.
There's one problem with that too, because the robot, at least with a micro mouse, they turn a lot. so when you look up to the screen, you have to turn to change the orientation, unless you're one of those people who can read in any orientation without turning your head.
So you put a compass on it and have it do it.
Auto rotation. Well, that's easy. You just have a gyro. Then it won't change its rotation. It will stay in place, right, for the most part. What is that gyro and what is that turret doing on this robot? Oh, it's just for the LCD display.
And my laser that takes out the other robots.
Actually, a gyroscope it's amazing what people can do with gyroscopes. Okay, here I know I'm getting a little digressed here, but it's related to path planning and motion control, so I'm not totally digressing from this discussion. Before GPS, how do people navigate? How do airplanes navigate and know where they are before GPS satellites are up there? There are two ways. Okay, this is declassified. I know I can talk about this because it's not classified military information anymore. Okay, there are two ways. One is to use the stars. But in the good old days, before the optics and the sensors, and the computation power becomes, really, really, at this point, where it's technology has matured, they have a really hard time, finding stars, even though the sky may be clear, do the calculation to triangulate, the location on Earth was a big deal. I mean, it was not easily done. These days, they can do it even with clouds. I think they use either infrared stars or infrared radiation from stars, so they can actually see through clouds and use stars for navigation purposes. So if stars is not an option, what is the other option? Gyroscopes. Okay. So basically, what a gyroscope is when you spin up a gyroscope and you put it inside, a high precision, ball bearing type of, cage, the orientation of the gyroscope will remain exactly the same, no matter how the airplane is, rising, falling, turning, yawing, and whatnot. So what you can do, if you know the speed of the airplane, and you also know the direction of the airplane, you can do what they call dead reckoning. Dead reckoning is just saying, okay, I know I have moved forward this many steps, and then I turn, I move this many steps, and then I go back this many steps. So without even using any external feedback, I should be able to calculate my current location. That particular approach is called dead reckoning. And dead reckoning relies on gyroscopes and also force sensors, so the airplane or the calculation, the machine can calculate using acceleration, deceleration, orientation, and all those information can be used. We were just talking about integration, earlier in the lab, and this is a practical use of integration, because all you have to do is to figure out, okay, I'm sensing acceleration in this direction for this long, so I must be at this particular velocity, at this point, and it's pointing to this way, and so on and so forth. And it's amazing how accurate they can make dead reckoning in the past. They can automatically land airplanes using just dead reckoning. They have that sort of precision. Now these days we don't have that sort of precision anymore because we don't need it because of GPS. So we can get a little bit lazy these days because of GPS. A robot needs to do motion control, which means a robot needs to control the speed of the motors. Now this part is a big topic all on its own, depending on what kind of motor you're using. Some requires more logic and feedback and processing power. Others are much simpler to deal with. Okay, it depends on whether you're using stepper motors or whether you're using DC motors or DC brushless motors versus brush motors. So motion control is something that requires constant attention from the computer's perspective. Path planning, even though you can go straight at a certain speed, where are you going? Where are you at this point? Okay. You have to read the sensors to do your path planning, because now you need to figure out where you are. Are there obstacles in front of you, and so on and so forth. That's sensor interpretation, self-monitoring and diagnostics. Is anything overheating? what is the condition of the batteries, and so on and so forth. So all of these things happen, they all have to happen at the same time. You cannot say, oh, hold on a second here, I'm communicating with a Bluetooth device. I stop everything else and just sit there, do nothing, and then communicate. You cannot do it, okay? You have to communicate while everything else is going on. Are we kind of having a sense of why multi-threading can be useful in a robotic type of platform? In many type of platforms, it will still be useful because there are multiple things that you have to do at the same time. Can we do all this without multi-threading? The answer is yes, but very, very painfully. Because what you have to do is to slice everything into small chunks. Okay? In other words, you have to maintain a Bluetooth or communication tick subroutine. The communication tick subroutine will be a big, will have a big switch statement to maintain its own state. So every time you call communication tick as a function, as a subroutine, it will remember where it was last time, use the switch statement to go to the right case, and within that case, you only want to specify about this much code so that it doesn't take up too much time. And then at the end of that case, you have to remember, next time I come back, where should I go next? So you have to use a variable to store the value of the next case statement. So that the next time you come in, it knows not to continue with the same state as this time, it knows where to go next time. And then you have to do everything like that with all of these. Your program is not going to read like a program anymore. Every single one is going to be a big, huge switch statement with a lot of cases inside. If you're not careful and put some kind of a loop inside the case, not thinking how much time the loop is going to take to execute, the timing of this entire thing can be off. Okay? That type of programming has a name, or my previous employer gave it a name. It's called a big loop program. Because the entire program consists of, guess what? One big loop. You go back to the beginning of the loop, you give the communication take one call. You give motion control take one call. Path planning take one call. So the entire loop, big loop, is just calling all these subroutines, giving quote-unquote a tick or a small chunk of time to each subroutine to execute. It's up to the subroutines to chop up what it needs to do in chunks. The next question is, go ahead.
That sounds a bit like DOS.
Yes, it's worse than DOS because there's no such thing as I'm giving up control now, and when we come back we can continue the rest of the program. When that's Windows 3.0 up to I guess the NT kernel. Now, but there's another problem with this approach. The big loop approach has one big problem. Motion control and sensor reading and potentially sensor interpretation, they are time sensitive. In other words, if you try to control a stepper motor and want to maintain a constant speed, the motion control tick needs to occur every 20 milliseconds, plus or minus maybe 1 or 2 milliseconds, because otherwise the timing will start to be off and then your speed will be uneven. The question is, can you guarantee this big loop can complete in exactly 20 milliseconds? Not faster, not slower, by a millisecond. It'll be extremely hard to do it. Maybe in some cases you can do it, but it will be very, very hard to do it. Anytime you change the logic of any piece here, you can potentially change that timing. And you can also have certain states of one of these particular ticks where it is rare to happen. So you can test your program all day long and it maintains that 20 millisecond time frame. Only once in a blue moon that you have to get to one execution path that you did not test, and that takes up 5 milliseconds more, and it messes up the timing of your stepper motor control subroutine. And if it's off by 5 milliseconds and your stepper motor is going at a high speed, that is just enough time to stall the motor. And bad things can happen when that happens. Okay, so big loop programming is definitely not desirable. So basically, I have the same thing here. So what we want to do is we want each task that we want to do here to be its own sequence of operation, and therefore to be its own thread, because we don't want to have a big switch statement, chop it into small chunks, and so on and so forth. So that's why each thread becomes its own subroutine. Plan path is its own subroutine. Typically, in a robotic situation, these are mostly infinite loops because you don't actually get out of a thread because the robot application does not end typically. Okay, so the next question is, now that we have so many things that we have to do, how do we make sure that each one gets its own chance to execute? Each task needs to get its own chance to execute. Round robin describes the behavior of the threads sharing the same processor in a circular fashion. Okay, so you get a chance to execute, I get a chance to execute, that thread gets a chance to execute, then it's back to you again. Okay, so we just have to go in a round robin fashion. Now, when you do it in a round robin fashion, how do you say it's your turn? I mean, every thread wants to hog all the processing resources, right? So how do you say, oh, okay, I guess I'm done for now. Here's your chance to execute for a little bit. Well, there's actually usually a function called yield. Yield means I'm done for now. I'm giving up processing resources, so the next thread gets a chance to execute. This is actually how Windows 3.1 applications are written. If you have a Windows 3.1 application and it has to go through some heavy-duty calculations, there is a call, similar to yield, to basically say, well, I'm not going to be done for a while. Why don't I take a break at this point? Let the next Windows application to get some chance to execute. When it's back to me, I'll execute some more. In other words, this is self-governing. Okay, it is up to each thread to voluntarily give up control so the next one gets a chance to execute. Are we doing okay so far with this type of multi-threading? But this will not work with hard real-time constraints because, what if one thread decides to take up a little bit too much time? There's no guarantee of timing anymore. Okay, let's just say that you are a thread, and I'm a thread. Okay, you are handling Bluetooth communication, you are handling sensor readings, and I'm handling motion control. Okay, and we are trying to share processing resources this way, round robin and voluntary basis. In other words, you're the Bluetooth part. You do a little bit of work. By the time you get to a certain point, just say yield. Okay, it's up to you now to do some sensor reading. When you're done with sensor reading and do some processing, you say yield, and then it's my turn to do some motion control, and I'm responsible to control the stepping of the stepper motor, or do motion control with a DC motor, whatever. Okay. Your stuff is not exactly time limited. If you respond, 40 milliseconds too late to an end user, it's not even noticed. Okay. So from your perspective, whether I give control back to you every 50 milliseconds or so or not, is not important. As long as it's not that up to like half a second, the end user won't notice any difference. From your perspective, maybe you're reading some insensitive, sensors. That's a funny word. Sensors that are not really critical. Let's say you're monitoring the temperature of the battery, and we have a big battery. Well, big batteries cannot change temperature very quickly, so whether you're reading every 100 milliseconds or 150 milliseconds makes almost no difference whatsoever, because the temperature of the battery simply cannot change all that quickly. But to me, controlling the stepper motor, whether it is 20 milliseconds versus 22 milliseconds, makes a big difference, because that will make the rotation of the stepper motor really jerky. Okay, in some cases, the motor can stop spinning altogether because there's not enough torque. Okay, so but I'm at your mercy because either one of you can choose. I think I can just do some more calculation here, take up 2 more milliseconds, which is nothing to you, but to me, those 2 milliseconds will cause the motor to stop. okay, and the application just fails at that point. Okay? So in this case, with voluntary yielding to share resources, between the threads, is okay as long as timing is not critical for everybody. But as long as you have one thread that says, I need to execute my code every 20 milliseconds sharp, okay, this approach is not going to work. Are we doing okay so far with the limitations of this approach? But it's very easy to implement. This approach, just voluntary yielding is very easy to implement.
When you do voluntary yielding like that, how do you know how much time you're giving up before it comes back to you?
You do not know because it's up to the other threads to yield also before it gets back to you. And that's why in Windows 3.1, Windows 95, and I believe 98 is the same way. If an application is not playing nice with other applications, it can quote-unquote lock up the other applications because the other applications simply do not get execution time from the processor. But when we run Windows, it's half a second is not a big deal. So that's why we have preemptive thread change. Now, when we talk about preemptive thread change, we are basically saying, well, let's talk. We can have multiple levels of threads. Okay, we are starting to prioritize. Let me see if that is its own topic. Priority based. Okay. Okay. Preemptive means the real-time kernel can maintain time. Okay. The real-time kernel in these cases, I have 3 more minutes. The real-time kernel in these cases will have its own timer. It's a hardware timer. In other words, the software cannot mess up the timing. So the real-time kernel I didn't kick the rock too hard. Okay? Just for the record. So in the real-time kernel, what happens is there's an internal hardware-based timing mechanism that takes like every so often. So when you have a thread that is time sensitive, you can say, hey, I'm a very time sensitive thread here. I have to execute every 20 milliseconds, period. Okay? So it's the same situation here. You're still handling the Bluetooth communication. You're still handling the low frequency sensor reading. I'm the motion control thread here. So you two can do the same things that you used to do. Okay, you'll be voluntarily give up control to each other, and then you guys have one round robin loop. But I'm different, okay, because I'm time sensitive. So I just tell the real-time kernel and say, give me execution time every 20 milliseconds. Well, okay, you are doing a Bluetooth thing. It's taking a little bit longer to process, the user input or format, the output to send to the user. And my time is up to execute my code already. What do you think the kernel is going to do? The kernel is going to take control away from you forcibly. So you don't get to yield anymore to give control back to me. The kernel will take control away from you even without you yielding. So I get control every 20 milliseconds. When I'm done, guess what? The control is back to you. Okay? So in this case, it's called preemptive because the kernel can preemptively take control away from a thread to give it to another thread that needs control right at that point.
So at that point, you are not in the round robin at all. It's just he and I are in the round robin.
Correct. I'm not in the quote unquote background anymore. I will be more kind of interrupt driven because when the timer takes at a certain time, I get control anyway, even though you guys are not ready to give up control. And that's what the next slide talks about, priority queues. Basically, it says you can have different round robin queues. You can have one for low priority stuff, one for mid priority stuff, and one for high priority stuff. And the way it works is, if you have any thread in the high priority queue that has something to do, nobody else is going to get execution time until all the high priority threads says, okay, we all have nothing to do at this point. Then we get to the mid priority queue where all the threads within that can get its execution time. When no high priority or mid priority queue threads have anything to do, then we drop all the way down to the low priority threads only at that point they can execute. But if for timing purposes or any other reason, either a mid or a high priority thread needs to execute, it will be preempted from the low priority. And you can have as many levels as you want. It doesn't have to be high, medium, or low. You can have 20 different levels, 10 different levels, 5 different levels. It all depends on how you can structure and say that these threads are of the same priority. These threads are all of the same priority, and these threads are all in the same priority. Within the same priority, it is still round robin. It is still saying, okay, I'm done, give it back to you, I'm done, give it back to you, and so on. And my website is not working. So it is time anyway. It is time to get out of this class. So we'll kind of continue with this discussion later. This is really kind of like a backdrop for the multi-threading stuff that we are talking about, but in a more low-level type of discussion, because we are looking at the mechanism of how threads are actually implemented and how it's actually used in this type of situation.
But Dr. Tack, I don't understand. Like, if the high priority stuff is still around robin, aren't all the same problems still in effect of the 2 milliseconds here or there?
Yep. Yep.
I guess we don't care, but,
So among the high priority stuff, how do they designate?
Yeah.
Well, that's a topic for next time, because within the same priority level, you can still have what we call time slicing. So time slicing is a mechanism also provided by the kernel, and what it does is it's telling the kernel and say,